KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
Free bus for LKG to 8th standard.
Free, hygienic and nutritious food.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Education Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, now we are going to discuss focal length of spherical mirrors. Focal length of spherical mirrors. Okay, right. In our last class, we discussed introduction to ray optics and then what is reflection. Afterwards, what are the laws of reflection and terminology related to reflection and basically, so basic terminology what we needed to discuss the situation in case of reflection or some other consequences, right? So like what is point of incidence, what is plane of incidence, what is the incident ray, what is the reflected ray, what is the angle of incidence, what is the angle of reflection, what is the normal, what is the point of incidence, right? And what is principal axis, what is focus, what is the center of curvature, what is pole, right? These are all we discussed. Okay, so why I am saying all these things means the terminology is very important for us when we are going to discuss the ray diagrams. So the ray diagram gives the position of the image, size of the image and nature of the image, either in case of plane mirror or curved mirror or in case of lens, whatever it may be. Okay, the terminology is very important. So I repeat once again, in our last class we discussed about the introduction to ray optics and reflection of light, then laws of reflection along with important terminology, right? Now in continuation to that, we are going to discuss focal length of spherical mirrors. Focal length of spherical mirrors, right? So focal length, first of all, what is meant by focal length? Focal length is the distance from pole to focus. Focal length is the distance from pole to focus. So while explaining sign convention in our last class, I told you all the distances should be measured from pole onwards, right? So in that sign convention, I explained you many points, but this is the one of the important point, that is all the distances should be measured from pole onwards. Okay, right. Focal length is the distance of focus from pole. Focal length is the distance of focus from pole onwards. Okay, right. Spherical mirror. Spherical mirrors are the examples of curved surfaces, right? So spherical mirrors means obviously convex mirror and concave mirror, right? So convex mirror means what we are using just beside the driver of a vehicle, so which is rear view mirror, we can see in our daily life. Concave mirror means like which you can also call it as shaving mirror, that also you can see in our daily life, right? So the applications of mirror very vast. So there are more applications due to the spherical mirrors, right, and plane mirrors also, right? But here our discussion is about spherical mirrors, right? So I told you two applications, not only two, there are many applications. Even in case of telescopes also, in case of reflecting telescopes, we are using these spherical mirrors. Okay, right. So mirror means it is a reflected surface. So plane mirror means plane reflected surface. Spherical mirror means curved reflected surface. Curved reflected surface, right? Just for point of observation, you can see here it is concave mirror, because representation also important, no? So on the blackboard we are going to represent concave mirror like this and convex mirror like this. Okay, right. So what I am saying is, rays which are incident at points close to the pole of the mirror, rays which are incident at points close to the pole of the mirror and make small angles with the principal axis or paraxial rays. So these two lines giving information about what are paraxial rays. What are paraxial rays? So keep in mind, what are paraxial rays? The rays which are incident at points close to the pole of the mirror. The rays which are incident at points close to the pole of the mirror, right? And make small angles with the principal axis and make small angles with the principal axis, right? So keep in mind, if you take the parallel, if you take this light ray, when which is parallel to the principal axis, what is the angle, ma? 0. The angle will be 0, right? So angle need not be 0, but it should be very small to decide what are the paraxial rays. Our discussions almost for paraxial rays. So either proof for some of the quantities, I mean like radius of curvature and mirror formula and lens formula, and even to discuss the image formation also, mostly we are going to take paraxial rays. Okay, if you are not taking paraxial rays also, our discussion will be different, but it is not the situation. But what I am saying is, what are paraxial rays? Rays which are incident at points close to the pole of the mirror and make small angles with the principal axis are paraxial rays. Next, principal focus is a point on the principal axis. Principal focus is a point on the principal axis of a concave mirror or convex mirror where the reflected rays converge or appear to diverge. Where the reflected rays converge or appear to diverge, right? So converge, C-O-N-V-E-R-G-E. See this spelling, ma? C-O-N-V-E-R-G-E. So converge or appear to diverge, right? So just when I am saying information, you should not feel like information. You have to imagine every point. That is important in physics and most important in optics chapter, right? So principal focus is a point on the principal axis of a concave mirror or convex mirror where the reflected rays converge or appear to diverge. So here, so these rays are going to converge, and here these rays are going to appear to diverge. Okay, so here you can see the two pictures, ma. So here if you observe carefully, here converge physically, right? So these are the incident light rays, these are the reflected rays. So converge at this point, that point is principal focus. Suppose if you come here, it is appear to diverge, right? So these are the diverged light rays. So here, right, you can see incident 1, 2, 3, 4, and this one also, like you can feel like a light ray. So even if you allow a light ray passing along like a principal axis, right, so then it will retraces the path. So it is the incident, that is the only reflected. So coming back, that's why in place of principal axis you can imagine a light ray. So here appear to diverge and here converge physically, right? So here you can expect this is the point of principal focus and here this is the principal focus. My request is, you please understand the difference between concave mirror and convex mirror regarding the principal focus. Here all are solid lines. Incident rays are solid lines here and here, but here in case of reflected rays also those are solid lines, but here reflected rays are, see here, what is this dotted lines. So it is virtual, not real. Here these are the real, right? So because why? Because the rays are going to meet actually at focus, that's why solid lines. Here rays are not meeting actually but appear to meet. So these are the diverged reflected rays. If we extend back, they will meet at a point at focus, right? So which is the focus point. Okay, so that is the point where all reflected rays appear to meet, not actually meet. Next, if the parallel paraxial beam of light, were incident making some angle with the principal axis. If the parallel paraxial beam of light were incident making some angle with the principal axis, the reflected rays would converge. From a point in a plane through F normal to the principal axis. This is called focal plane of the mirror. So this is very important for us while solving the problem. Yesterday in the last class itself I told you what is focal plane, but now again he is talking about focal plane, and you can see this picture here. See the red light what I am showing you. So this is the focal plane. Right? So which is normal to the plane of the board, right? See here. See, I will repeat once again this information. If the parallel paraxial beam of light were incident making some angle with the principal axis, the reflected rays would converge or appear to diverge from a point in a plane through F. Normal to the principal axis. This is called focal plane of the mirror. Focal plane of the mirror, right? So see here it is. So here you can see there is some angle between this incident ray and principal axis, right? So here also there is some angle between the incident ray and principal axis, but here laws of reflection also obeying by the mirror. It is what? Concave mirror, right? So here angle of incidence is theta. It is the normal at this point of incidence, and it is that what joining a line from point of incidence to the center of curvature acts as a normal. So this in the last class I told you, I am repeating once again. So here the line joining from center of curvature to the point of incidence is the normal to that point of incidence. So here angle of incidence is equal to angle of reflection. Angle of incidence is equal to angle of reflection. So it is theta dash, means it is also theta dash. Similarly, consider another incident ray. So here it is the incident ray, it is the reflected ray. So here also the same thing. This angle is equal to this angle, that is angle of incidence is equal to angle of reflection. It is theta double dash, means this is also theta double dash. So this is the focus where reflected light rays will meet. So this is the focus. So which is a focal plane? It is the center of curvature. I already told you. It is the pole. So this diagram is showing focal plane, which is perpendicular to the principal axis, normal to the principal axis. Okay, right. Now we are going to see relation between two things. One is focal length, another one is radius of curvature. So that is actually radius of curvature is equal to 2 into focal length. What is focal length? Focal length is the distance of principal focus from pole onwards. Focal length is the distance of principal focus from pole onwards. What is radius of curvature? Radius of curvature is the distance of center of curvature from pole onwards. Radius of curvature is the distance of radius of curvature is the distance of center of curvature from pole. Distance of center of curvature from pole, right? Here, in case of either defining focal length or defining radius of curvature, defining image distance, defining object distance, whatever it may be, one point you keep in mind, I am saying the distance. So it is the actually it is like shortest distance, right? So like displacement. So in coming picture also I will show you. I mean in the next class I will show you what are the things. Okay, what are the things I will show you. So there itself you can understand what is object distance and what is image distance. It is simple, as much as simple. Now itself I can show you. Suppose this is the pole, no, it is focus, no. So from here to here, this is the distance. So which is the focal length? Suppose it is center of curvature, no, it is pole, no. So from here to here, this is what? Radius of curvature. Radius of curvature. So one relation satisfied by the ray diagram, generally in practical, right? Not only in the picture, in practical, radius of curvature will become equal to 2 into focal length. 2 into focal length, right? Okay. So now we are going to prove this. Radius of curvature is equal to 2 into focal length. See this. So it is the concave mirror. It is the principal axis, incident ray, reflected ray, normal, right? It is F, it is F, focus, okay, right. So loss of reflection, it is angle of incidence, angle of reflection, it is theta, means this is also theta. So geometrical mathematics, when it is theta, this is also theta. So here it will be 2 theta. This is theta plus theta, 2 theta. When it is 2 theta, this is also 2 theta, right? It is for concave mirror. For convex mirror, the same situation will be like this. It is convex mirror. So it is the incident ray and it is the reflected ray. It is the angle of incidence. So the dotted lines, right, from center of curvature, the dotted lines from center of curvature here, okay. So it acts as a normal. It is the angle of incidence, angle of reflection. If it is theta, this is also theta, right? It is at point M, right? So when it is theta, this is also theta, it will become 2 theta, right? So it is the normal drawn from M to D, normal drawn from M to M onto the principal axis. This is the point is D is the point where this normal drawn from M met on principal axis, okay. The same situation here also. The only thing is, here it is concave mirror, this is the convex mirror, okay. It is theta, this is 2 theta, right. So try to understand the picture, okay, right. Next, so from these 2 pictures, that is one for concave mirror, another one for convex mirror, we are going to write from the ray diagram, okay. So this is what? Angle MCP is equal to theta. So this is MCP is equal to theta, and MFP, this is M, it is F, I already told you, right? It is P. MFP is equal to 2 theta, right? So one is theta, another one is 2 theta. Next, you know very well, tan theta is equal to opposite side by adjacent side. So from this triangle MCP, so it is what? MD by CD. But here itself I want to say one important point. See here, for paraxial rays, almost this D will coincides with P. If you take, actually for visibility purpose, here we took some distance from this incident ray to the principal axis, but in practical, if you take this paraxial rays, I mean this ray close to the principal axis, and when it is paraxial ray, so these two will be coincide almost, so there must be no gap. That's why here we are taking P as a D, right? That is the only thing. It is one of the practical oriented assumed thing here that we are applying here. Then we can write it as tan theta is equal to MD by CD, and tan 2 theta is equal to md by fd, md by fd, right? Tan theta is equal to md by cd and tan 2 theta is equal to md by f into d, okay, right? So here itself, for smaller value of theta, which is true for paraxial rays, so I already told you which is true for paraxial rays, tan theta is identically equal to theta and tan 2 theta is identically equal to 2 theta, right? So when tan theta is identically equal to theta and tan 2 theta is identically equal to 2 theta, substitute these two things here. Then what can we write? Theta is equal to md by cd and 2 theta is equal to md by fd. Okay. So now we can write this one. Md by fd is equal to 2 into md by cd. Md by fd is equal to 2 into md by cd. These two will get cancelled. Fd is equal to, right? Fd is equal to cd by 2. Fd is equal to cd by 2. What is Fd here? This is what? Focal length. So that is small f. What is cd here? Which is what? Nearly equal to radius of curvature. With our assumption, it is radius of curvature. Then finally I can write it as r is equal to 2f. So which is a important question for 2 marks in our board. And neat point of view, this formula is important for us. R is equal to 2f. That I can prove, right? Already here we have written radius of curvature is equal to 2 into focal length. Radius of curvature is equal to 2 into focal length. Okay, right. Next, here itself we have to discuss some important points. These points helps us when we are in a discussion about ray diagram. When we are in a discussion about ray diagram. Okay, right. See this. First point, the ray from the point which is parallel to the principal axis, the ray from the point which is parallel to the principal axis, the reflected ray goes through the focus of the mirror. Focus of the mirror. You can see this example. See this. This is the ray which is parallel to the principal axis now. Which is parallel to the principal axis. After reflection, how it is going? It is passing through the focus. See, observe carefully. It will pass through the focus of the mirror. Okay. Next, the ray passing through the center of curvature of a concave mirror. The ray passing through the center of curvature of a concave mirror appear to pass through it. Appear to pass through it. See here. This is what you can say here itself, right? Okay, you just imagine, So actually it is the normal. If you imagine in place of normal a light ray which is passing through the center of curvature, then automatically it retraces its path, either concave mirror or convex mirror. But when the ray of light is passing through the center of curvature, it retraces its path. See this. The reflected ray simply retraces the path. The reflected ray simply retraces the path. Okay, that is next point. Here actually it is arrow, it is not continuation to the principal. It is arrow, right? Which is indicating the next point. Okay, see this. The ray passing through are directed towards. So in case of concave mirror or in case of convex mirror, whatever it may be, the ray passing through the focus of the concave mirror appear to pass the focus of a pass through. Otherwise, the focus of the convex mirror reflected ray is parallel to the right. I will explain you this third point, right? So this third point is reverse to the first point. Third point is as simple as such. It is reverse to the first point. So first point, what is saying? When the ray which is parallel to the principal axis before incident, after reflection it will pass through the focus. In third point, what he is saying? When the ray which is passing through the focus before incident, after incident, the reflected ray which becomes parallel to the principal axis. Parallel to the principal axis. That only he is saying. So he is talking about both concave mirror and convex mirror. That is the only difference. Okay, right. Next, the ray of light at any angle. The ray of light or the incident ray at any angle at the pole. The incident ray at any angle at the pole. The reflected ray follows the laws of reflection. So this yesterday also we discussed, right? What is the reflection and what are the laws of reflection? Yesterday itself we discussed for both plane surface and spherical surface, but here once again he is saying the incident ray at any angle at the pole, right, then the reflected ray follows the laws of reflection. So what are the laws of reflection? The angle of incidence is equal to angle of reflection. Next, what is the second law of reflection? Incident ray, normal and reflected ray. Incident ray and reflected ray lie in the same plane. Okay, right. So in this class we discussed what about the focal length of spherical mirrors in case of concave mirror and in case of convex mirror. Then what about focal plane? Afterwards, what is the relation between radius of curvature and focal length? Radius of curvature is equal to 2 into focal length. Radius of curvature is equal to 2 into focal length. Okay. Afterwards, we proved how that relation is correct, that is R is equal to 2F. After completion of that, we discussed some important points which gives information about nature of reflected ray. Nature of reflected ray after incidenting at a point on a curved surface. Even it is applicable for plane surface also, because so the last point is also telling about laws of reflection. Okay, so which is also true for plane surface and curved surface. Okay, right.